Welcome back, Algebra 2 class. In this video, we'll continue looking at transformations. This time, we'll specifically look more at exponential functions and logarithmic functions. Just as a heads up, there are going to be 3 slides on this for each of the 3 big transformations we'll be looking at, and each of them is going to have a table like this on it. So what you may want to do is on each slide, pause me for a second, copy down the table, and then follow along as I annotate. The first big transformation we're going to be looking at is the vertical stretch or compression. So just to look at this with a general function first, what a vertical stretch or compression does is if we start with some function f of x, okay, again, this is where we start. In all of these examples, f of x will be where we start. And we want to get to some new function g of x. But we want to have g of x be stretched or compressed compared to f of x. All we end up having to do is multiply f of x by some number a. So we'll take whatever our original function was, we'll multiply the whole thing through by some constant a out front. And the effect that a has is that if the magnitude or the size of a is greater than 1, then this thing gets stretched out, right? Big A's will stretch out our function. And if a is smaller, if the size of a is less than 1, then it's going to get squished. Now keep in mind, this does account for negative. So for example, if a was negative 1,000,000, that falls into the size of a is bigger than 1 category. Now let's look at exactly what that means as far as some examples. So if I started with some function, f of x equals 2 to the x, as our exponential example, and I want to do a vertical stretch by a factor of 3. So this factor tells me just how much I'm stretching it out. A vertical stretch means that a has to be bigger than 1. So a vertical stretch by a factor of 3 is just going to mean, well, I multiply the whole thing by a 3 out front. Similarly, in order to do a vertical compression, right, I'm squishing my function down, it's getting shorter. In order to do a vertical compression by a factor of 1/4, I'm going to have to multiply my original function, which is 2 to the x, by 1/4 out front. Really similar thing happens with logs, right? We'll start with a parent function of f of x equals log base 2 of x. A vertical stretch by a factor of 3 again, we have to multiply by a 3 out front. And to do a vertical compression by a factor of 1/4, we're going to multiply by a 1/4 out front. Right, so nothing too crazy here. For vertical stretches or compressions, we just want to pay attention to we're multiplying by some a value out in front of our function. For vertical translations, how these end up working out is we start again with our function f of x. In order to vertically shift this up or down, what we do is just add or subtract some number way at the end. So we're going to call that number k in this case. If k is positive, right, if we're doing like f of x plus something, then we are shifting up. If k is negative, we're doing f of x minus something, then we are shifting down. So that was those 2 pieces right there. So again, we'll move on to some examples. If we start off with our same parent function, f of x equals 2 to the x, in order to shift that up by 3 units, all I have to do is add on that plus 3 at the end, right? Up 3 units does plus 3 at the end. If I want to go down, k has to be negative this time. So to go down 4 units, I have to do a minus 4 at the end. Right? Notice how this doesn't really change. You can still really easily find the parent function there because these are added or subtracted way at the end. Similar thing again happens with our logarithmic functions, right? We start with that same parent, log base 2 of x. In order to shift up 3 units, we're going to tack on that plus 3 at the end. Notice again, you can still find the original parent function really easily. In order to translate down 4 units, we have to subtract 4 at the end, right? That minus 4. Last transformation we're going to look at for this lesson is the horizontal translation. So this shifts our functions left and right. Now this one is, I think, the trickiest one to figure out. We talked about how horizontal stuff happened inside the parentheses when we were working with quadratics a lot. That's how we kind of described it, like we had to have like x plus 3, the whole thing squared. Well, what's really happening here is for a horizontal translation to happen, whatever your original f of x was, you have to go ahead and everywhere you used to see x, replace it with x plus or minus some value. So in order to do a horizontal translation, your original f of x has to be replaced by some function where you have, instead of just x in there, you have x plus or minus something. And similarly, if h is greater than 0, we're shifting to the right. If h is less than 0, we're shifting to the left. However, this kind of has the opposite effect of what you would think because of this minus sign here. This minus sign plays a big role. And we'll see exactly what that does in a second. So in order to do a horizontal translation to the right 3 units, right, I want my graph to go to the right, I actually end up with a minus 3 up in this exponent here, right? 2 to the x minus 3. Now there are a couple things to point out here. First of all, notice that the minus 3 is no longer way out at the end. It's no longer added on at the end. It's right up here with x in the exponent. And that's because, remember, going back to our general function, the plus or minus a number has to be right in there with x. Anywhere you used to see x, you should now expect to see x plus or minus something. Now the other thing is, you'll notice there's a minus 3 here in order to go to the right. That's kind of the opposite of what you would think, but again, it's because of that minus, right? H is actually positive 3, but if we're doing x minus positive 3, that's just x minus 3. On the other hand, if we want to go to the left by some amount, we end up with a plus sign in there, right? So to go to the left by 4 units, we end up with x plus 4. For our logarithmic example, right, we'll start with our same parent function, log base 2 of x. Same idea here. Wherever I used to have just an x, I now have to have x plus or minus something. So to go to the right 3 units, think the opposite of what you would normally expect, right? In order to go to the right, I have to have x minus 3. In order to go left 4 units, I actually have to go x plus 4, right? So again, anywhere for horizontal, anywhere you used to see an x, you're replacing it with x plus or minus something.